I like the mnemonic oil rig. Oxidation is loss of electrons and reduction is gain of electrons. Now, often, but not always, oxidation is going to correspond to the gain of bonds to oxygen, and the reduction is going to correspond to gain of bonds of hydrogen or loss of bonds to oxygen. And so, yes, it's kind of helpful to think about, okay, oxidation, more bonds to oxygen, reduction, less bonds to oxygen. But thinking of it that way is going to get you into trouble when things aren't quite so simple. And more fundamentally, you're missing the point of redox, which is about those electrons. Oxidation, loss of electrons or electron density. Reduction, gain of electrons or electron density. We can make things formal by calculating the oxidation number. There are two main methods to do this. The first is you subtract the number of valence electrons owned if it were ionic from the number of valence electrons the atom has in its neutral state. So that's just the column or group of the periodic table. And that'll give you the oxidation number. Alternatively, start with the charge of the atom and then consider each bond it's involved with. If the atom wins the electron tug of war, that is, it's more electronegative, subtract 1 from the charge. If the atom loses the electron tug of war, that is, it's less electronegative, you gain 1 in your charge. If it's a draw, so you've got a bond between the same atom, no change in number. You also don't get a change in number with a protonation or deprotonation. That is not redox. But if you compare two molecules and you increase the oxidation number, that means it's been oxidized. A decrease in the oxidation number means it's been reduced. And the sum of the oxidation number should always equal the formal charge. If we're comparing molecules, we typically see things move in chunks of 2, because if you gain a bond to a more electronegative atom, that's going to be a +2. A gain to a bond to a less electronegative atom, that's going to be a -2. If you have an atomic form, the oxidation number is going to be 0. The oxidation number of hydrogen is almost always going to be +1. The oxidation number of oxygen is almost always going to be -2. And if all that's changed between two molecules is protonation state, the oxidation is the same for both of them because, by definition, a proton has no electrons to give or take. But our biological fuels do have electrons to give and take, and so we see these oxidative reactions be used where we're passing those electrons from these different molecules in a series of oxidative reactions onto NAD+. When we do that, we generate NADH. The key place that you see this happening is in the citric acid cycle. We're generating a lot of NADH. That NADH can then be used in the electron transport chain to give you ATP. Voila. Redox.